Here's an application of colligative properties, determination of molar masses. The basic idea here is you prepare a mixture. So if you make the mixture yourself, you go to the lab, you know how much solute you're using, how much solvent you're using. So you know the mass of the solid and the solvent. Then you measure a colligative property. Okay? So in your Chem 110 lab, you're going to either be measuring the boiling point elevation or the freezing point depression. So what if you know the colligative property and you made the mixture? So from the colligative property, what can you determine? Remember, for example, let's say you did delta TF. That's going to be equal to minus KF times M, right? So you can go to the lab, you can measure the freezing point of pure water, and then measure the freezing point of the solution that you made. You can get your delta TF. You know the KF for water, so you can get the total concentration of solute particles. You'd be able to solve for the total molarity. So once you've done that, you should be able to calculate the total moles of solute particles because you know how much solvent you have, right? What's the definition of molality? Mole solute over kilograms of solvent, right? So if you multiply kilograms of solvent by the total molality, that gives you the total moles of solute. So your molar mass is whatever the mass of your solute was divided by the total moles of solute particles, okay? Grams per mole, that's your molar mass. That would be your average molar mass, okay? That's going to be exactly the molar mass of that's going to be the molar mass of your solute if your solute doesn't fall apart, doesn't dissociate, okay? If your Van Hoff factor is 1, then that would be your molar mass. If your solute splits into 2, then you have to, what? You're going to get twice as many particles, so you have twice as many moles, you end up with a molar mass that's lower, okay? So that's the average of the molar mass of the ions that you're getting if your solute dissociates. So let's summarize that procedure. So you measure your colligative property, delta TF or delta TB in the lab. You get your total molality. The osmolality is the total molality. How do you get from there? Delta TF is equal to KF times M, negative KF times M, right? So your osmolality would just be delta TF over negative KF. Same thing with the boiling point. You divide by KB instead. Now, gram solvent, how do you change grams to kilograms? 1 kilogram is 1,000 grams. So kilograms times osmolality will give you moles of solid. Okay? And you measure the grams of solute to begin with. So these are things that you measure in the lab. And then this is what you calculate from your result. So gram solute divided by moles of solute will give you the molar mass. Let's see if we have an example for that. Okay. A 2-gram sample of an unknown solid is mixed with 20 grams of benzene. Okay. Pure benzene freezes at 5.533 degrees Celsius. So TF star, pure benzene melts at or freezes at 5.533 degrees Celsius. Okay. Now, when the benzene was contaminated, when 20 grams of benzene was mixed with 2 grams of your unknown solid, it's found that the freezing point is now negative 0.87 degrees Celsius. And the KF, the cryoscopic constant for benzene, is 5.12 degrees Celsius per molality. Okay? So this is what you did in the lab. You took out 20 mils of benzene, 20 grams of benzene. Okay? Benzene is C6H6. And then to that, you added 2 grams of unknown. Okay? And so you measured the freezing point of that mixture. And you found that to be negative 0.87 degrees Celsius. And you measure the freezing point of pure benzene, you find that to be 5.533 degrees Celsius. You look up the KF for benzene, go look it up from a handbook. It's 5.12 degrees per molality. So what would be your molar mass for the unknown? How would we solve for this? Let's go back to our strategy back here, our diagram. From the colligative property, what do? We can calculate the osmolality, the total molality of solid particles. So let's do that first. What's our osmolality? It's delta TF over negative delta TF over KF. What's our delta TF? What's the freezing point of our mixture? Negative 0.87 degrees Celsius. What's the freezing point of our pure liquid? 5.533 degrees Celsius. Okay. What's our KF for benzene? 5.12. Okay. Don't use 1.86 here. When do you use 1.86? When you're using water, right? This is benzene. So if you're not using water as your solvent, you have to look up your KF. So in the case of benzene, it's 5.12 degrees Celsius per molality. Okay. By the way, you might see this written as degrees Celsius per mole times kilogram, because molality is moles per kilogram. Okay. So if when you look these numbers up, this might be shown as moles per kilogram. So you might see it degrees Celsius per mole per kilogram. Or the unit might be given to you as degrees Celsius per mole times kilograms, because your kilograms per kilogram is in your denominator. Okay, so I just want you to be aware of that. It will not always be shown as just little m, because little m is just abbreviation for moles per kilogram. Okay, and since you're dealing with temperature changes here, okay, this degrees Celsius, if you look it up, it might be shown as Kelvin instead of degrees Celsius. Okay, a 1 degree change on the Celsius scale is equivalent to a 1 Kelvin change. So keep that in mind. Don't be thrown off if you do see different units shown there. A Kelvin unit, as far as temperature differences are concerned, a temperature change of 1 Kelvin is the same as a temperature change of 1 degree Celsius. You don't add 273 or subtract 273, okay? Because we're looking at differences in temperature. Just to elaborate, 0 degrees Celsius is 273, right? 1 degree Celsius is how many Kelvin? 274 Kelvin, right? So a 1 degree change, if delta T is 1 degree Celsius, that's also 1 Kelvin. Okay. All right, so let's go ahead and finish this up. Let's see, what do we have here? What's our delta TF? Negative 0.87. So what do I have here? Negative, oops. Okay. Negative 0.87 negative minus 5.533, that's negative 6.403. Okay. So negative of negative 6.403. How many sig figs should I have here? This is addition and subtraction, so I have to stop at this second decimal place. So this is my last sig fig here, divided by 5.12 degrees Celsius per molality. That gives me negative, that's positive, so 6.403 degrees Celsius over 5.12 degrees Celsius per molality. Degrees Celsius cancels out. What would that be? 6.403 divided by 5.12, that gives you 1.25. So our molality is 1.25 moles per kilogram. That's our total molality, our osmolality. Are we done? Not what we're looking for, is it? You need the molar mass, right? So let's see, what do we have so far? Our molality is 1.25 moles of solid particles per kilogram. Okay? How do we actually get the total moles? What's the definition of molality? Mole solid per kilogram of solvent, right? So molality times kilograms of solvent will give you moles of solid. Okay, so let's see, go back here. Molality times kilograms of solvent will give you moles of solid. So how many moles of solvent do I have? Let's see. Let's say moles of solid particles is molality times kilograms of solvent. And that gives us, what's our molality? 1.25 mole per kilogram. How many kilograms of solvent do we have? It's 20 grams of benzene, so it's 20 grams. That's 0.02000 kilograms. Okay? That's 4 sig figs right there. So how much is that? 1.25 times 0.02, that's 0.025 moles. 3 sig figs, so 0.0250 moles. Now that we know how many moles we have, what's our molar mass? This is solid, okay? Moles of solid. And so our molar mass is grams per mole. So grams solid over moles of solid. Okay, so that's equal to, how many grams of solid do we have in the problem? 2 grams. You're given 2 grams of solid, 2 grams of your unknown. 2.00 grams divided by the moles of solid is 0.025. And so that gives us 2 divided by 0.025, 80 grams per mole. 80.0 grams per mole. Okay? So that's how you determine the molar mass from a colligative property. And so there's more problems for you to work on. I think I'll let you work that out yourself. So this might be a good time to take a break.